It gives me great pleasure to introduce Mary Sheeran as our opening speaker for today. So Mary is a professor at Chalmers in Sweden, and I guess she actually does not need any introduction. She's been in this area for so long. I'm really happy that she could come here to talk to us. And I don't know, I think personally the type of work that she does is very important and relevant for us because, I don't know about you, but most of the time when I go in front of students and have my functional programming course and they ask me, okay, that's cool, but what is the killer application for functional programming? And then I say, theorem proving. And everyone's like, what? How is that relevant to me? And the work that Mary does in some hardware design and acceleration are two things that allow us to go in front of normal people and be less embarrassed. So thank you very much, Mary, for the work that you do, and thank you for accepting this invitation.
I'm going to talk to you about hardware description and verification, so there will be something like theorem proving. But I want to start with a bit of history, because I think it's interesting, when you've been around as long as I have, to think who are the giants on whose shoulders we are standing when we do this kind of thing. So I looked up, where did the idea of describing circuits using Boolean algebra come from, and when? And the answer is that it comes from Claude Shannon's master's thesis. This is a bit worrying. From MIT, and he wrote it in 1937. And it was about the idea that you can use Boolean algebra to discuss relay circuits. They weren't really, gates and the stuff we know about then. They were actual physical relays and things. And he made a list showing, the correspondence between relay circuits and the propositional, and, or, and not, and so on. And then at the bottom, he designed an adder, a binary adder. So those two pictures at the bottom are of, if you know what, a full adder and a half adder. And you can make a binary adder by combining one full adder and a lot of half adders. So this is probably the first binary adder that was published anywhere. And it's a very interesting master's thesis. And if you're interested in old documents, go away and have a look. But I found another, so of course you all know that Claude Shannon then founded information theory and coding, and he's considered the father of the digital age and so on. But he also thought of this idea about Boolean logic. It's fantastic. But I found another hero who I had actually not really heard of. And this is Irving S. Reed. You've probably heard of Reed Solomon something and Reed Muller something and so on. But Irving S. Reed in 1952 wrote a beautiful paper, or it's actually an engineering note, he called it, on the use of Boolean algebra in logic design. And I think he was actually a functional programmer, he just didn't really know it, and there wasn't any functional programming at that time in 1952, but he writes things like, to a first approximation, we can describe a binary computer as a set of two-state memory devices functionally connected by an information processing network. That's exactly what I'm about to do. And then he says things like, it is customary to represent the logical structure of a machine by block diagrams. Unfortunately, you cannot calculate with block diagrams. They are merely expository devices. Everyone will agree that it would be helpful to be able to represent machines by sets of equations for which we know simple rules of transformation. You see, he was a functional programmer. And so at that time, they had or, not, and this is a picture of how to make exclusive OR from those gates. And the GT thing, the thing called GT is and, inv is inversion, and the joining of two arrows is OR. And so this is how you make an XOR gate out of 5 other gates. And then he explains how you can use Boolean algebra to reason about the behavior of such a circuit. And then he goes on to talk, so that was what we call combinational logic. And then he goes on to talk about flip-flops. I don't know if this is the first introduction of the word flip-flop, but he talks about state-holding elements, and he says, well, we need a way of thinking about state-holding elements too. So he writes, at this point it becomes necessary to explicitly indicate the dependence on time of the variables in our discussion. Expressions like A of t represent voltage or current or whatever physical quantity is as used as the realization of our 0 and 1 at particular points in the machine at time t. And then he talks about, for definiteness, let us assume we are dealing with a clocked machine, i.e. a machine in which the changes in state of flip-flops must occur at discrete times, the times at which the clock pulses occur. And then, as seems to have been typical of the age, he kind of he becomes snarky about what Shannon had done earlier. So he says, you know, Shannon did something. However, Shannon's theory took no account of the dependence on time of the states of a computer. Therefore, while it led to an analysis of networks of gates, mixers, inverters, and the rest, it did not permit an analysis of flip-flops. The theory was no substantial help in designing counters, adders, and so on. So I have a new hero, Irving S. Reed, 1952. And then the question is, what happened next from a kind of programming language person's point of view? And actually not much, not much happened for a while, except that in the 60s, APL, which I suppose some of you have heard of. Have you heard of APL? Well, not all of you. Oh dear. Go away and Google it. Okay, it's a programming language developed by Iverson, who won a Turing Award for his work on it. And he used it, he wrote a famous paper called Notation as a Tool of Thought, which you should all read. But APL in IBM was used in a very serious way as a hardware description language in the 60s. And they described the whole of the IBM System 360, and they did experiments where they generated circuits and hand-designed them and compared the size and so on, published about this in 1970. So it was quite like a golden age of hardware description in the 60s. And then what happened? So I studied electronics, engineering science with electronics and theoretical computer science in the 70s. And it was block diagrams all the way. There wasn't a single hardware description language visible at that time. And so I thought, okay, I'll go and do formal methods somewhere. And I went to Oxford to do formal methods. But in 1980, a very important thing happened for circuit design, and that was the publication of this book called Introduction to VLSI Systems by Mead and Conway. And this is described as the book that changed everything in circuit design, hardware design, because it opened up hardware design to not only the priesthood of the small number of people who knew how to do hardware design, but also to normal people like computer scientists. And it led to the development of Intel and MIPS and all kinds of things. There were multi-project chips, there were courses, there was excitement. I attended a course about this when I was a master's student, as did my supervisor, who was Peter Henderson, who, among other things, invented lazy evaluation at the same time as several other people. And he also studied ways to describe pictures. So I was away just trying to describe the pictures on the front of Mead and Conway. I was making circuits and laying them out and implementing them and so on, but he was describing Escher pictures. So there's another paper you should all read by Peter. But luckily, in 1977, Turing won John Backus won the Turing Award and wrote a paper that appeared in 1978 called Can Programming Be Liberated from the von Neumann Style, a Functional Style and its Algebra of Programs? How many of you have heard of this paper? Oh, good. And so he introduced the language FP and talked about an alternative style, functional style of programming founded on the use of combining forms for creating programs. And those combining forms are what we now call high-order functions. And I was trying to, at the time, think, how should I describe circuits? And I read Backus's paper, and there were these combining forms, and they were exactly the right thing for describing circuits, the structure of circuits. So that's where the idea of describing the structure of circuits using higher-order functions came from, at least for me. So I developed a language called MuFP, which was like FP, but on streams. You heard about streams yesterday from Ivan. So it was like the same idea, FP, but where the values that flow in the programs are streams. And I studied the algebraic properties of these combining forms. So this is an example of the kind of law I wrote down. It said, if you look at the top of the diagram, if you can push an F through a G and get two Fs, then you can also push a bunch of Fs through a linear array of G's and get something that has F's in between the G's. Okay, so why might that be useful? Well, if those F's are, for example, unit delay elements, then you can talk about pipelining, for instance. So the whole name of the game then was to try to reason about circuits containing delay elements or dealing with time in FP instead of in MuFP. When can we make reasoning easier about the sequential things? When can we reason as though we were reasoning about combinational things? And we had great fun. But people did find the notation a bit strange. And then I even made it worse by having a relational version of this language, which I called Ruby. This was before the other Ruby. The other Ruby people once wrote to me and said, "How dare you use our name?" I said I was there first. But there was not much effect on the outside. I got my doctorate, that was good. Well, not much effect on the outside. Actually, we did use MuFP in a group at Plessy, and they really did use it for doing a design of a systolic array, and they loved it. We gave them a symbolic simulator, so that was great. But then they got bought by another company in the middle of the project and shut down. So that was the end of that. That's what industrial collaboration can be like. So what's the reality today? I had to choose the Swedish Wikipedia page about hardware description. This says hardware describing languages. And there's only 2 languages on it. Okay, I had to take it from a few years ago. But still, what I want to indicate here is that when you look on Wikipedia or when you look in the real world, the hardware description languages that are used in practice are the ones that we as functional programmers would perhaps not love, like Verilog and VHDL and System Verilog. So why still try? Why am I still interested in this question as a functional programmer? Well, I still have contacts with Intel, and one of the talks I saw recently from one of the people there showed this slide from DARPA in 2018, but predicting design cost for ASICs, for circuits implemented on silicon. And if you look at the rightmost column there, it's the design cost about now for an ASIC, probably quite a large ASIC, and it's over $500 million. And that's the design cost. This has nothing to do with the cost of building fabs and all those other parts. And typically today, verification takes more than 60% of design cost in design of advanced ASICs. And in many places, perhaps in Intel, it's 70%. So now there's often more verification engineers than design engineers. So there's still something to do, and it's still interesting to think what we as functional programmers can contribute in this world. So let's go back to the beginning to read. We're going to describe circuits. I'm going to talk at the lowest level of circuits about combinational blocks and unit delay elements. And I'm going to use higher order functions, which you all know and love, to plug together blocks to make larger circuits. And we're also going to study, to some extent at least, the algebraic properties of these higher order functions. Let's go back to our exclusive OR gate. Okay, I want to just show you, what can you do in Chalmers Lava, which is a piece of code written in the year 2000 by Kuhn-Clausen, but it has been updated a little bit since, but not very much. we can take Reid's diagram of an exclusive OR gate and we can just write it down in Haskell. So we have now then a Reid exclusive OR. It's going to be a function which takes a signal, or this would be similar to the stream that you had yesterday from Ivan. It's going to take a pair of signal bools and it's going to produce a signal bool. And I've written down for each gate in the picture, I've written down a call of the relevant gate. And this is the structural view of how to describe circuits. Every time I write down a function, it will become a function in the circuit. So it's a slightly strange view of describing circuits, but it works very nicely, at least for me, and for many people, I think. So this is the description of the exclusive OR. We might want to ask the question, is it this, in Lava we do have XOR built in. So I can ask the question, is Reid exclusive OR exactly the same, the output for the same inputs as exclusive OR 2? And I can ask the question on a particular input. We called 0 and 1 high and low. I kind of vaguely regret that these days. So I can ask, what do I get if I give it high and low? And the answer is high. There's a little hint here. I wrote the word simulate here. So this is a deeply embedded language in Haskell. So what's happening behind the scenes is that we run our function, it creates a data type, which we can then do whatever we like to. Among other things, we can walk over it and make net lists, we can generate formulas and so on. There's some type class cleverness too. So I can ask things like, if I take prop read and map it over all of the domain, all the possible inputs, do I always get high? And the answer here is yes. So we can be pretty sure we did make an exclusive OR gate here. But we could also generate a formula for input to Minisat, which incidentally we also made in the group while we were making Lava. And it will say valid. So this now is a kind of proof that we really have an exclusive OR gate. And what happened behind the scenes is that a file containing Dimax CNF formula got fed to Minisat, and Minisat gave back an answer. And this formula indicates at the top that it has 10 variables and 24 clauses, and there's a smaller example, so you can see what it looks like. So we're kind of set up. We can play at least with combinational circuits. We have a SAT solver plugged onto the back. So we're kind of on the way. What are we good at as functional programmers? We like higher order functions, and we like to think of new, at least I like to think of new and interesting higher order functions. Let's think about some higher order functions on lists. I want to think of a kind of column major order. Think of this as a single array or list, and I'm going to read it in this order, the leftmost column, then the next column, and so on. Because I want to use this as an illustration of what some of the higher order functions I use are. So then I'm going to have a higher order function called interleave, or ILV, and that's going to apply a function to all the even elements, number indexed elements, and all the odd indexed elements of a list. And 2 is going to apply a function to the first half of the list and the second half of the list. And now we can begin to study algebraic properties of these things. For example, it turns out that 2 of ILV of F is the same as ILV of 2 of F, as illustrated beautifully by this diagram. This diagram is almost a proof. So now we can use this kind of higher order function to describe interesting circuits. So here's an interesting circuit by Batcher. You've probably heard of odd, even, merge sort by Batcher. Batcher also invented bitonic sort, and both are described in this paper from 1968, which has a lot. I often put the number of citations a paper has in a box, in a oval, so that people can think, I should go away and read that paper. So Batcher described, first of all, an odd-even merger. And he gave its kind of recursive decomposition using these diagrams. So it's actually the interleave of two odd-even mergers, and then it's a bunch of comparators applying to everything but the first and the last inputs. So let's write that down in our new higher order function. So we can describe the odd-even merge just as a recursive function. It's going to take as input the comparator, which is going to be list-to-list, and it's going to produce a list-to-list function. So at size 1, it's just going to be the comparator, and otherwise it's going to be the interleave of a half-size odd-even merge composed with odds. What is odds? Odds is this pattern in which you place comparators on all of the pairs except the first and the last, and we can just write down small bits of Haskell to describe that behavior. We can first describe evens, which applies a two-input function to each adjacent pair in the list. And then we can describe mid, which says apply a function to everything but the first and last, and so on. Now, people who think about sorter networks have their own notation these days for describing them. So this is the notation that's used. The inputs are on the left, and they're going to flow towards the right. And the vertical wires with a circle on the top correspond to a comparison. And the values flow from left to right, and they go through these comparators. So that's a picture of the odd-even merge for 16 inputs. On the blue part is a picture of that odds thing. And that can be used to make a sorter by recursively applying two half-size sorters at the beginning and then having the odd-even merge. And this in total has 63 comparators. Let's just think about a couple more combinators and then move on. So here's another of those combinators. Q, I call this Q for reasons of not being able to think of better names. And we can just describe Q by composing a little permutation on each group of 4 with ILV. And then I had another one that I called V. Okay, I was not doing very well on names. But we can, once we have 2, ILV, Q, and V, it turns out we can describe lots of interesting networks. And really, it turns out we don't really need any more than those 4. So this is a network by Canfield and Williamson, which claims, it's made of ILV, Q, and odds, you might say. It's claimed to be good because it should have the shortest wires when you make the sorter. So higher order functions are good for giving us an understanding of the literature of sorting networks, which is often only presented with block diagrams. In case you're bored and need to think about something different, there's a famous 60 comparator sorting network by Green, which I have studied again and again to try to understand how did he do this, and can I make it large? Can I make a recursive version of the same thing? I have wasted so many hours on that. But I think we don't know in many cases how best to do sorting. So that's if you want something a black hole, go away and think about Green sorter. So I'm going to skip some of this here. Now, for a given sorter, it turns out that we can play one of these tricks. If you have a sorting network, it doesn't matter on what types you want to run the sorting network. You can check it by plugging in Boolean sorting components. This is called the 0-1 principle. You can read about it in Knut, for example. And that's very handy for us because we have a SAT solver. So we can very easily then verify that these networks do actually sort. So here I cut something out of a very old file of mine where I had passed the Canfield and Williamson sorter, and I had checked it for 2 to the 5 inputs. Notice that we are verifying behavior for a fixed size circuit here. And then I wrote, these are quite hard proofs. Sort check of 10, that is 2 to the 10 inputs, takes longer than I'm willing to wait. I don't know what it would do on this Mac these days, but at least we have a means of verifying these kinds of very regular circuits. And once we have a way to describe very regular circuits, we can begin to play our kind of functional programming tricks. So if we're going to generate a sorter, we also have the means to think about generating related but smaller networks. So this is a median network. It has 25 inputs, and it produces its median output. So this is the output that you would get if you sorted everything at the middle point, and then everything above should be less than or equal, and everything below should be greater than or equal. But we don't care about the ordering of those parts. Okay, so this is like a sub-network of a sorting network. And we can use cleverness during the generation. So we have an embedded language, so we kind of have a circuit level and we have a Haskell level. And we can play tricks because of this fact to decide as we do the generation whether or not to add comparators or not. And this enabled me to go down from 99 comparators to 96. Now you may think, okay, that's not important. But actually, there's a piece of C code that was the motivation to this that contains 99 compare and swaps, and that is used in median filtering. And therefore, it's actually quite interesting to be able to do it in 96 instead of 99. I tried telling somebody this, but he paid no attention. And how did I do this cleverness? I exploited this two-level thing, and I have what I call shadow values. So there's Haskell level values and there's circuit level values, and I can maintain in the Haskell level information about how sorted things are, and then I can place small circuits that apply themselves or apply a circuit to the shadow values and decide what circuit to put in at that point based on the knowledge that's encoded in the Haskell level values. So this was the trick that I had to use to get from 98 to 96. So this piece of code says, I want to sort 3 inputs, but I might not care about some of the outputs, in which case I can drop one comparator. So that's what it's about. So that's quite cool. It's interesting to see what is the difference between an embedded language and a powerful host language together compared with just having a single language. I believe quite strongly in this embedded language idea. Another example that I've been obsessed with is prefix sum or scan. If we have a component that takes 2 inputs and produces A plus B both downwards and to the right, then we can make just a linear array of them, and this will produce the sums of all of the prefixes of that network. And the people who study prefix sum have their own notation for fixing them. So we take some of those dots and we just pull them downwards in order to indicate the time at which the computation happens. So this indicates that the leftmost dot happens first, and then the next one, and then the next one, and so on. And you might think, okay, that wasn't a very interesting circuit. But if we know something about the plus, for example, that it is associative, then we can begin to play some tricks. So the circuit on the left does A plus B first, and the circuit on the right does B plus C first, but then it has to fix up the output to get a 3-input prefix. We haven't gained much at this point, but if we then add on the left another input and another dot, we'll see that now we can do a 4-input prefix sum in 2 steps of time instead of in 3. So we have compressed the time, and in general we can do prefix sum in log depth. So for 2 to the n inputs, we can do it in depth n at the price of a lot more components. So we can trade space and time. This is a famous network by Ladner-Fisher. On the left of that network, it's kind of spread itself out more in that the dots come towards the end, therefore there can be fewer of them. So there's lots of games we can play. And I wanted to understand what is the smallest possible minimum depth prefix network. And I thought somebody must know, so I tried to read the literature, but nobody appeared to know. So I thought, okay, I'll use search. And so I after much fun, which I'll say a little bit more about, I found the answer. I figured out how to make the smallest possible prefix network. And so I wrote a paper in JFP. I didn't make big claims. I just said this is the smallest known, because I was not able to prove it to be the smallest. And about 2 days later, a mathematician from Moscow wrote to me and said, your network matches my lower bound. And he said, I've written a paper about it. I haven't published it yet, and it's in Russian. And I love the way he later wrote in the English version, Sheeran discovered a sequence of 2 to the n prefix networks via computer programming. And I thought to myself, okay, am I annoyed or not? There was quite a lot of thought involved. How did I do it? So it's a recursive network. So it's got 2 recursive calls in it, P and Q, and in fact those T's over there on the top are also small prefix networks. And so the whole key to figuring out how to do it is to figure out the sizes of all of these things. So I used lazy dynamic programming to figure out what should be the sizes of the networks at each level as we go down through the recursion. And this is a beautiful example of why functional programming is good. I would be entirely incapable of writing down an imperative dynamic programming code to do this, but I could just write it down in Haskell, and it all worked. It was wonderful. And I did this over many sizes, and I also generated those pictures that you saw of the networks, and I pored over the resulting pictures, and in the end, I could just see the answer. Right? I could see what the pattern was. So I was then able to write a very small piece of Haskell that doesn't involve any search to generate my network. And there's another trick that can be used here, in that I can do a correctness check here also. If you take such a network and you give it singleton lists, 0, 1, 2 as its inputs, and it then produces the 0, 0, 1, 0, 1, 2 out, that is, you use the list append as your operator, then this will be a proof that you really have a functioning prefix network. So this is another example where we found an easy way to do a proof of something apparently hard. This is related to parametricity for those of you who know about such things. So here's an example of the network. It has 256 inputs and 773 operators for that size. But the point I want to make here is that if you have a notation and the means to tinker, to play, then you can invent new things. That's the whole point, I think, of domain-specific languages. And you might think, okay, this is all very abstract, nothing to do with me. But actually, if you look on any microprocessor, there are lots of prefix networks on them. So the reason I became obsessed with them is that I once visited Intel, and they told me to talk to about 10 different people, and every one of them was thinking about prefix networks because they are so important. The hotspots on this picture are the integer arithmetic and the floating point arithmetic, and the red parts are, I would bet, the prefix networks. So fun things can be done with almost regular structures. So what does Lava give you? It gives you symbolic simulation and various interpretations. You can produce net lists, pictures, you can produce VHDL net lists, formulas, and we do formal verification using the SAT solver and a method called k-induction with distinct states. So that's a complete model checking method that was also developed in the process of making Lava by Stolmark. And so that's, you might say, the old Lava. There is a new version of Lava. There are many Lavas. But there is a new version, you might say, of Chalmers Lava being developed in Cambridge called Blarney. And it's now connected to an SMT solver rather than a salt solver. It's connected to Z3. And I have a very, very clever intern from ENS Paris who has really, really beefed up their verification backend because he looked at k-induction with distinct states and how to use quantifiers there, and he just thought of a new way of doing it. That is just much better. This is what happens when you get clever students as interns, right? It's fantastic. But But I'm not as happy as I should be. And there's still a problem that I have not managed to solve, and it's how to trade space and time in sequential circuits. I would like to be able to take my circuit. I always imagined sitting in lava and taking my circuits and thinking to myself, that linear array, I'm going to fold it up over time. Right, I'll only put one value of that and I will fold it up over time. And I'll have some slow clocks and some fast clocks. And it should all be easy. But it's not. Okay. So neither any of the old stuff, MuFP or MyRuby, or any of the lavas are satisfactory for this problem. So I thought, okay, I'll think about it again. And I went back to an old paper about Ruby that Wayne Look wrote about serializing. And this is a lovely paper because it takes an example. He proposes how to think about serializing circuits, folding them up, and then he shows it all on a convolver example. But he uses ideas that I had a long time ago, and I made a mistake a long time ago. So this talk is an admission of a mistake. When I was thinking about how to think about serialization, I didn't distinguish slow and fast delays. There was only one kind of delay. And so I had something that I call bundle. In the vague part, it says, in order to explain slowing in Ruby, we will introduce a new primitive which describes the demultiplexing of a sequence of values into n separate signals. So think of a sequence of values flowing in on the left, A, B, C, D, and it's going to produce A, and then the number 5, and then number 9, and so on. So A, E, B, F, and so on. So it's going to take a single stream in and produce 4 streams out. And I thought, okay, that didn't work. What will I do instead? Well, you could think of having as the formal basis on which you do your verification just be unit delays controlled by related clocks. Clocks whose frequency is related. That's probably not too hard to do, but it doesn't need it. So I have a simpler solution, I think. And I think the answer is to use sized space and time sequences. So I used lists earlier as what I call the sequences over space. But these days I'm going to use sized vectors. So for example, a sized vector of size 4 of signal of bool is going to be 4 Boolean streams. A0, A1, A2 will be one of them. So we'll have 4 elements at each clock cycle. So that's 4 Boolean streams over space, just like we had with lists. But now I'm going to introduce time vectors. And those time vectors are going to be, so time vector of size 4 of signal of bool is going to be, again, 4 Boolean streams. But they're going to be interleaved over time. So at each of the big time steps, we're going to get a sequence over small time of elements of each of the components. So they're going to flow in the circuit over time, but we'll have, in this case, 4 of them belonging to one of the big clock cycles. So once we introduce timed vectors, I can correct my error in the definition of bundle, and I can say, oh well, bundle is now going to be something that takes a time vector of size n to a space vector of size n. And what does map over space mean? It means replication over space, just like map over lists did before. What does map over time mean? What does map T mean then? Well, I'm just going to define it in terms of map over space. I'm going to say it's bundle composed with map S of F composed with unbundle. And I'm going to rename bundle to TS, time space. Bundle is too long. And this is the thing that's called slowdown, that circuit designers use as a trick. So map T of F is going to apply F to streams, but interleaved over time. It's very hard to think about. Somehow space things are easier to think about, but actually it's very similar. And designers implement slowdown. You can implement map T of F by taking F and taking every unit delay element in it and replacing it by a sequence of n unit delays. And then you get something equivalent in behavior to map T of F. So it's a trick that is known to, the people who think about systolic arrays and so on. So this is my proposal. It's a very small and simple proposal. I'm going to introduce time sequences, and I'm going to talk about trading space and time. I'm going to fold circuits up in ways that do not introduce new sequential reasoning, because that's the key. We can't afford, the formal verification tools still talk about one step at a time. So we can't afford to reason about these things with fast clocks in at the level of the fast clocks. We have to do something clever. And that's what we can do by the introduction of these time sequences. So we are going to introduce some fast delays, but only in a very safe way. So we're not going to give the user single fast delays, for example, to put in. We're only going to put them in safe places. I'm just going to show you one more. I showed you map T, which is a bit hard to think about. I'm going to show you one more, which I'm going to call rho of T. One more higher order function, and then I'll be ready to round up. Let's think a bit, though. I'm going to creep up on rho T. So let's say we have a sequence, or a linear array of functions f that just compose one after the other. We can express that using map in this rather strange way. So we can relate the repetition of a function to map, as long as we do some extra stuff with wiring, okay? And I'm going to make a little bit of a change here. So now I would like to figure out how to describe this diagram in Haskell. That's not too hard. What is the yellow thing? It takes an n sequence. No, it takes a value at the bottom and an n sequence on the left, and it produces an n sequence and a value. So it's a kind of shift. Okay, so I can just write it down. So repetition of S, I can make by a single shift and a map, and I can just define the shift at the bottom. So the shift is going to take A and B's, and then it's going to produce as its output init S of ABs and the last of ABs, where ABs is just A cons Bs. Okay, so it's going to take, ABs is going to be a long sequence, and it's going to produce all but the last element of it and the last element of as its output. So it's a kind of shift. And this kind of equality holds even if those blue boxes have state elements in them, because all we're doing is explaining the wiring, you might say. And it also holds if you add some inputs and outputs on the blue boxes. So that's nice. So we can write down rho S, which was the thing on the left on the previous slide, in terms of shift and map. Okay, there's a bit of zipping you have to do here, but that's all. I should add as a kind of aside on the theme of making proofs easier, that while I was preparing the talk, oddly enough, I was thinking, okay, how should I reason about rho S kind of circuits? I discovered an old paper of mine that tells you how to do it. It's very weird. It's a beautiful paper. It has 7 citations, right? Nobody ever read it. But it tells you how to add additional subformulas to proofs. It was using Stallmark's prover plus some arithmetic to enable you to prove properties of linear arrays of various kinds, including, for example, multipliers, which are hard to prove. So that's cool. So that's rho S. And we can use rho S, for example, to make Shannon's adder. Okay, that's an add. Well, actually, I only used full adders. Okay, I cheated. I only used full adders and I put a carry in. But this is how you make an adder. You make a row of full adders. And now I'm going to do something that worries some of you. So I made rho S, and it seemed believable. It seemed. Now let's switch to time sequences. So I just took all the S's and turned them into T's. And some of you are, that's a horrible thing to do, but some of you know other ways to do it, but okay. So now this is row over time, which is much harder to think about, but actually it's just the same. And the question then is, what is the shift over time? And it turns out to be what Wayne Look in that paper I told you earlier is a counting multiplexer. So now all these values are not over space, they're over time. But I carefully chose the shift so that it turned into something reasonable to do over time. So now we can describe the repeated use of f over time. And so it's got a map T in it, which in reality we will probably implement by doing the trick with replacing the unit delays by sequences of them. But there are no fast delays visible, so the only component that involves the fast delays is this counting multiplexer. But from the point of view of the big time unit, that's a combinational thing. So now we can reason about fancy sequential behavior as though it was combinational, and that's a good thing. Okay. So the verification is going to be just unrolling those microcycles, and it all works because we know the sizes of things. So this is a nice use of size types. The pesky dependent types appeared. Okay. And this all seems to work quite nicely. We can implement map T. If f is combinational, incidentally, then a single f will do for map T. We have to be careful about the types. But if we have, for example, the smallest circuit I could think of, if we have map T of delay of 0, then we can replace that by delay of 0, but that 0 inside is a different type. It's of type TVN of A. So that's going to mean we're going to compose a number of faster unit delays. And so this is related to a famous paper on slowdown by Lysis, Rose, and Sachs, which is also a beautiful paper. So we can go back and we can write down Wayne Look's examples. So here's the original one with the row S. It's a convolver. And now I can say, okay, I want to take, instead of row S, I'm going to have row T of row S. This is quite hard to think about, but the types help. So if n is k times m, then I had to add some types here. I had to talk about the W prime here, which is going to be a TVK of an SVN of something. So it's a time sequence of a space sequence of things. So you can kind of express access patterns in this way, so that's quite nice. And then we end up with something with a map T of row S in it. This is attempting to illustrate that. And then we will very likely replace the map T by taking the delay elements and replacing them by sequences. And it's a very simple idea, but it actually seems to be very sweet. Why didn't I think of it before? I'm not sure. Maybe I just didn't have sized types available. I'm a late adopter. Related work on this is, I was inspired by a paper in PLDI 20 called Etherling, which is, again, trying to think about the same ideas and introduces time sequences. But I think they get it a bit, it's not right. There was a BlueSpec, some of you have heard of BlueSpec is another hardware description language. There's a BlueSpec library about these kinds of folding up, and a recent paper by Greaves, who's the person who has released an open source BlueSpec compiler. And it turns out that Marc Pouzet, who's one of the synchronous programming people, Lust and Skade and so on, has been thinking about exactly the same kinds of things, like identical. And he's in a setting similar to what Ivan was talking about yesterday, where he's making software for controlling aeroplanes. So there's the certification question. So he's actually made a type system based on a polynomial representation of sizes and so on, which allows him to do much of the same things without the heavy machinery of dependent types. But I have to say that it's actually quite usable to have sized sequences. There's a number of GHC plugins that make it bearable. It wasn't bearable before. And I think those came from Clash, which is a hardware description language in Haskell. Haskell as a hardware description language. And my clever intern, who already reinvented K-induction, is also making a FPGA implementation of these ideas. Okay, so I hope I convinced you that at least hardware description might be interesting. If you want to go away and play, which I think you are the kind of people who would, Blarney is this version of Lava being developed in Cambridge. And it's got a layer of abstraction above these circuits and delay elements called recipe. And some people want to work at that level. And it's beefed up with the new K-induction stuff. It's not there by default at the moment, but it soon will be, I think. And Matthew Naylor, who's the person who's making Blarney, has used it to describe a classic 5-stage pipeline as a standard. So he's in an architecture group. So the Blarney is just a tool to help them do their architecture research. And so he's proved some end-to-end properties about this component. And he's used Haskell to describe interfaces. So he's using Haskell types to describe interfaces and protocols and so on in a way that's beautiful. So there's going to be a paper about that soon, I think. So if you want to play, go and play with Blarney. Of course, you might also just use Clash. I have to say, I haven't used Clash. Clash is Haskell for hardware description, but is not an embedded language. It's a language all of its own. It has sized space sequences. I may discuss with them whether they're interested in sized time sequences. And BlueSpec itself, in a variant that's Haskell-like, is also interesting. And BlueSpec these days, the company works a lot on RISC-V and developing various kinds of RISC-V. In association with BlueSpec, there is something that I think you'll all love, and it's called BlueCheck. And it's quick check for BlueSpec, but you implement it on your FPGA. So you're doing quick check type things, but you can put them on your FPGA so that it runs fast enough to do your testing on your FPGA, and it's super cool. That's the same person who made Blarney. So some people's names appear again and again. Matthew Naylor is his name. And why do I think it's interesting to tell you to go away and play with hardware? And I think there's a kind of new era coming in hardware related to chiplets. So what are chiplets? They're small bits of silicon that can be put together onto what they call a silicon interposer. So it's a way of allowing a system on chip to have parts of it designed by different companies or by different people. And another hero here, Andreas Olofsson, has a company called Zero ASIC, and he's making a design flow that allows you to take your own register transfer level code and use it to make one part of one of these chiplets and have it be possible to be put on a silicon interposer. So this is just in some way a democratization or making hardware design again available to more people, just like Mead and Conway did. This is a picture of one of these interposers and the various kinds of components that are already available. So when we talk to our Intel minders, they say chiplets, 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 learn about chiplets. So I think it's going to be possible to make small bits of ASIC for us ordinary people in a way that was not possible 10 or 15 or 20 years ago. So I would say, take the chance. Go and play. Thank you.
Thank you very much for your talk. We have time for a few questions. Can I just have a quick show of hands as to how many questions and where they are so that I can distribute properly? 1, 2, 3. Okay, good. Thank you.
Hello.
Hello.
Thank you for the talk. I have a quick question about functions. So in these expressions that you showed, your functions are Haskell functions, right? And when you target a different language, when you generate either hardware descriptions or in the case, for example, of Copilot, we can also target C, those functions get expanded by GSE.
No, yes, we do run those functions.
Right.
We do run them, but we run them only to produce a data type.
Okay.
So there's a data type that sits behind. Now there's a trick that I carefully glossed over. In the case where you have feedback in your functions, then you need to be able to tell that you have feedback and you can't just run it. And so there's something that we use called observable sharing there.
Okay.
Which allows us to take a function and turn it into a graph.
Okay.
And that's a trick. So that's a paper from around 2000 also. So I have to say that I don't even think about that when I'm writing down circuits. I just write them down. I make my feedbacks where I like. The original version of Lava used monads for the same purpose, and it was horrible. Mm-hmm. So it's very nice just to be able to name things and have this trick. So there's unsafe perform I/O going on behind the scenes, but the user doesn't have to think about it.
Okay.
Thank you for the talk. Just a small question in the designs. I wonder, is wire length any issue when designing hardware? Because that also introduces delays, of course.
Absolutely. So one of the things we had fun with was when I showed you the dynamic programming, it had a measure function in there. And one of the measure functions we used was the wire length, because at that time, when we first talked to Intel, they only cared about speed. And then later they cared about power. And so we tried to model wire length in order to find low power prefix networks. And we did find lower power prefix networks, but not to the extent that we hoped. So it wasn't, so there never became a paper because it was not, that's how it is with academia. If you don't win by a lot, you don't publish any paper. But we were able to do things like model wire length. So we later had a system called Wired, which was, so it's like a version of Lava that really takes account of wires. And that's very nice. That was made by Emil Axelsson. So that's worth looking at if you're interested in the very low details.
Okay, thank you.
Thank you very much for the talk. I had a brief question about using fast clocks and slow clocks. You showed us that you can model this using unit delays and that you don't expose the unit delays for the fast clocks to the user. But how does that actually work when you compile this to run this and produce this data type? Because you have these fast unit delays inside, for instance, the shift combinator. But then the user might themselves also use unit delays elsewhere directly.
So we haven't really done this. I mean, we are in the process of doing the generation, but I don't want to expose the fast. I'm only going to expose delay, single unit delay, and that's the slow delay. That's the only thing the user is going to get. But they will get row T, right? So they really get shift T. And that would just have to be generated using the fast delays. But that's all. So there's no visible use of fast delays that the user can control. Because as soon as you add a single fast delay anywhere, it messes everything up. And then you have to do your reasoning around that clock. So I want absolutely not to allow that. Now, Victor, my intern, he's a bit concerned. So we don't completely agree about the API yet. So that's why we're a bit slow here. But I think that controlling expressiveness for the user is probably okay. We'll see. We have to do lots of examples to see.
So does that mean that once you end up with this intermediate data type, that you do some kind of replacement, say, so because you need to know how slow the slow clock will be.
So the intermediate data type will contain fast and slow clocks. And then that will be used to generate the Verilog. There's still some questions about the interface to the downstream tools. But it does turn out that FPGAs at least do offer the ability to produce a smallish number of related clocks. So that seems to be okay. But if you want a large number, it probably doesn't work. It's clear that FPGAs are not really designed for doing this, but somehow we will be able to do it anyway.
Cool. Thank you very much.
Hello, thank you very much for the talk. So you mentioned how finding these diagrams that represent these prefix networks helped you find good solutions to these optimization problems. And do you know of any good algebraic descriptions that represent these diagrams that sort of capture some invariance of them and that allows you to reason about those diagrams? And the second part would be that, for example, in the case where you took this serial diagram and you looped it around itself, because these kind of remind me of these certain classes of monadic categories that arise in mathematical physics. And do you know of any algebraic descriptions of those?
I probably don't. So I think Dan Gika would be the name that occurs to me.
Pardon me? Can you repeat
Dan
that?
Gika.
Dan Gika. Okay.
Has done this kind of thinking, I think, about circuits and diagrams and categories. And so I think if you're looking for something in that direction, that might be a good place to look. My approach to analyzing these descriptions is always to do what I call non-standard interpretation. I always just run them on various different kinds of inputs. You know, inputs representing delays in, or inputs representing lengths of. So I do a very naive, but it works. You know, so for my purposes, those kinds of analyses are quite good, because at least I know that I'm analyzing the thing that will also generate the real circuit. So there aren't two separate representations, which I'm a bit afraid of having.
Thank you very much.
Hi, thank you very much for the talk. So you showed how using the size time sequences makes it easier to verify computations that are distributed over time. And I'm wondering if it also helps in the optimization on the design side of things to, if you're distributing a computation over time and space and you want to optimize for certain metrics like throughput and latency, does it help to automatically generate the optimal circuit?
So I think then I would have to do exactly the same kind of trick as I did for the prefix network and use search again. And I haven't tried that yet. And I guess the search space is pretty big. I mean, that's what, in a way, what the Etherling people were doing. So they're searching based on a context for a good implementation. But they have feedback free. I mean, they have delays, but they don't have any feedbacks. So it's somehow a simpler problem that they are trying to solve. Once you add feedbacks and delays, then things become quite a lot harder, I think.